All right, so I want to solve this problem with this person in the chair. She's pulling herself up at a rate of 2 feet per second squared. So let me write that down. So her acceleration is 2 feet per second squared. And we're given in the problem her weight, the weight of the painter, and we're given the weight of the chair. And she's pulling herself up at 2 feet per second squared. So we're using British engineering units in this problem. Let me quickly draw this. Not the best picture. But anyway, she's pulling herself up. And there's a couple of ways to solve the problem. And really it's going to depend on how you define the system. I'm going to define the system as consisting of both objects because if she's pulling herself up, then both her and the chair have the same acceleration. And if that's the case, then first thing I got to do is identify all the external forces acting on the system. So let me draw this again. Let me make a slightly better picture or bigger picture. Okay, and so here's the painter. And what's touching the system? Well, there's two ropes touching the system. Okay, there's one rope here touching the system. And the other one is here. We're going to assume that the pulley's massless, the pulley's frictionless, and that rope doesn't stretch, and the mass of the rope is negligible. And so the tension on both sides of the pulley is the same. The only non-contact force then is gravity. It's the weight, well, it's really the total weight of the system. And the total weight of the system is 128 plus 32, 160 pounds. And so all I got to do now is sum the forces in the y direction. Up is positive, down is negative. And I have two tensions upward minus the total weight equals mass times acceleration. Okay, so I'm given the acceleration, I'm given the weight, that tension is the force I'm applying to lift myself up. Okay, so let me solve for the tension. I'll do it very quick. I get the total weight plus ma over 2. That's the force you have to apply. That's going to be this tension and this tension. If we put some values in, well, the total weight is 160. Now, what's the total mass of the system? The mass is in slugs. And so I'm going to take the 160, and I'm going to assume g is 32 feet per second squared. Times 2 feet per second squared divided by 2. 160 divided by 32 is 5. 5 times 2 is 10. 10 plus 160 is 170. 170 divided by 2 is 85 pounds. So this is the force she has to apply to pull herself upward, such that her acceleration is 2 feet per second squared. Now, what is the force on the pulley? In other words, if you're trying to hold up that pulley, what's the force holding up that pulley? Well, if you draw a free body diagram on the pulley itself, the pulley isn't moving. But if you drew a free body diagram on the pulley, here's the pulley. Okay, here's the axle of the pulley that's holding it up. There is a tension here downward, another tension here downward. They're both 85 pounds, and then there's the force of the pulley upward. That force of the pulley upward is the sum of these two, which is 85 plus 85, which is 170. Okay, so that force is 170 newtons. Now, after 1 second, she pulls so that the chair goes up at a constant speed of 2 feet per second. So what force must she pull on the rope? Well, if she pulls herself up at a constant speed, A is 0. So we can set A equal to 0 here. And then 160 over 2 is 80. So when her speed is constant, she applies a force of 80 pounds to pull herself up. Okay, what I'm going to do now, I want to do part A of the problem again, but I want to do a little bit differently. So I want to show you something. So I want to keep this equation somewhere. I don't have a lot of space on my board, but I want to write it right here. And this m is the total mass of the system. So maybe I should put a sub t here. That's what I should have done from the beginning. So this was using the system as chair plus person. Now I'm going to do it differently. I'm going to define my system as the person. In fact, I'm going to have two systems. One is the person and one is the chair. So, here's the chair. First question is, what's touching the chair? And what's touching the chair is this rope. What else is touching the chair? Well, the person is standing on the chair. And so the person is exerting a downward force on the chair. Is it equal to the weight of the person? No. Okay. In fact, I want to call it N. And it points down. The other force that we have is the weight of the chair. Now let's draw the forces acting on the person. What are the forces acting on the person? Well, the person's standing on the chair, and so there's a normal force of the chair on the person. This is the reaction force to this. Okay, so this is force of person, force of chair on person. This is the force of person on chair. They're action-reaction pairs. Okay, so this acts downward, this acts upward. They're the same magnitude, they're just in opposite directions. So I'm labeling them the same. What else is touching the person? Well, not only is the chair touching the person, but the rope is touching the person. Those are the only two contact forces acting on the person. The non-contact force, well, is the weight of the person. The complication now in doing the problem this way is I have this unknown. But if I wanted to determine the normal force, this is what I would have to do. So let me sum the forces in the y direction on the chair. Up is positive, down is negative. So T minus N minus the weight of the chair equals the mass of the chair times A. Let's sum the forces in the y direction on the person, on the painter. We have T pointing up, we have N pointing up, we have the weight of the person pointing down, and then the mass of the person times A. They're going to have the same acceleration. Okay, so now I have two equations and two unknowns. And by doing it this way, I can solve for N if I wanted to. I'm not going to do that here. If you want to, you can go ahead and solve for N after I'm done with this. Okay, but it's not a hard problem to solve for N. So how I'm going to solve these two equations simultaneously? I'm going to add them. Look at what I get when I add those two equations. These two forces, which are internal when I define the system as consisting of the chair and the person, they go away. And so I have 2t minus the weight of the chair minus the weight of the person is equal to the mass of the chair plus the mass of the person times A. Well, this is the total weight of the system. And this is the total mass of the system. So as you can see, I get the same equation. Okay. It's just that I got to this a longer way, but this works too. And what the advantage is of doing it this way is that it will allow me to solve for the normal force. And so I think this is a very instructive example. I'm working with free body diagrams and analyzing two different systems. And the math is pretty straightforward.